All right, so in this lesson, we're looking at working on solving problems that involve volume of pyramids. Pyramids are a little different from our prisms and our cylinders because they come to a peak, which we call an apex point, and their bases can be different shapes. So in this first one, the base of the pyramid is rectangular. All of its sides are going to be triangles. So for a pyramid, its sides are always triangle, but its base can pretty much be anything. Here in the middle, we see a pyramid that has a square base. And here we see a pyramid that has a triangular base. So all of its sides are triangle. We call that a tetrahedron. And so here, that's important because when we're finding the volume of a pyramid, what we're going to do again is have to find the area of the base, our capital B, like we do for prisms and cylinders. So if you remember for a prism and a cylinder, that our volume is base area times height. Notice we still have base area times height, but now we have to multiply it times a third. And that is really because it's like taking, say, a rectangular, let's take this, let's say you had like a rectangular prism. And let's say that you were good at sculpting stuff, okay? So you're a sculptor, and it would be like cutting away all of this portion of your prism. And so that would leave 1/3 of the prism left. So this is like 1/3 of it. This is 1/3 of it. And what's left for our pyramid is 1/3 of what we start with. And so that's where this 1/3 comes from. Because if we start with a prism and cut things away to create a pyramid with the same base, then we'll have 1/3 of the original volume. All right. So this kind of outlines to just some stuff. So if you know that your base is a rectangle, then your base area becomes length times width, but you still have the 1/3 and the height of the pyramid. If you have a square-based prism, then the base area is like length times width, but we often call it side times side or side squared. And if we have a triangular based pyramid, this is the one that's a little bit more involved because our base area is the base edge of the triangle, shown here, times the height of the triangle, which is perpendicular to the base. There's our right angle there, times half, or divide by 2 if you prefer. So this can also be written as 1/3 times base times the height of the triangle divided by 2, then times the height of the pyramid. That's what this h is, the height of the pyramid. And notice for the height of the pyramid in each of these, it goes from the apex point straight down perpendicular to the base side. So for each one of these pyramids, our height starts at the apex, the peak, and goes straight down perpendicular, forms a right angle with our base side. All right, so again, most, if not all of these problems will involve some sort of a context situation, an application. Some of them may involve more than just calculating volume also, but an application of volume. And so we'll be doing several examples similar to problems that you will see in your assignment. But again, we won't necessarily do examples to match everything, but we will in our examples talk about all of the main skills and procedures that we will need to complete the problems we will be working with. All right, so we start by reading this problem. So the Great Pyramid in Giza, Egypt is approximately a square pyramid with the dimensions shown. So we have pretty much a square pyramid here, and we have this picture of our square pyramid over here. And the pyramid is composed of stone blocks, or it's made of stone blocks that are rectangular prisms. These blocks, so we've got these The pyramid is made up of stone blocks that are rectangular prisms. And these blocks have these dimensions: 1.3 meters by 1.3 meters by 0.7 meters. We are supposed to figure out about how many stone blocks were used to build this pyramid. And then our rounding instructions say round to the nearest 100,000. You're going to want to be super careful with your rounding instructions. Some of the things that I see people do is that they don't read carefully rounding instructions, and they always assume that they're rounding like to the nearest tenths or the nearest hundredths. And this is not true. The nearest 100,000 is in front of the decimal point. And we'll talk about more exactly where that is later in case you're not sure. So how would we start a problem like this? Well, if we know that this pyramid is made up of these blocks, then we need to know basically how many blocks would fit inside this pyramid. That's an application of volume, which is capacity, how much something will hold or can contain. So one of the things that we need to know is what is the volume of the pyramid. So here I'm looking at, okay, the volume of a pyramid. My volume formula for the pyramid is 1/3 times my base area times the height of my pyramid. And so my base area here, remember this is a square pyramid, so means square-based pyramid. And so my square has these side measurements of 230 meters each. So this is volume here is going to be 1/3 times, you can write it as S squared or just S times S if you prefer, that doesn't matter. So the height, H, remember, goes from my apex, my peak, straight down perpendicular, there's my right angle, to the square, which is the base. So that makes the 146 meters the height of this pyramid. So I'm going to plug in my numbers. So my volume of my pyramid is going to be 1/3 times my 230 meters squared times my height of 146 meters. So remember with like S squared, we're squaring the 230 and the meters. So 230 times itself, or 230 squared, is going to be 52,900. So this is 52,900 meters squared. And I want to show this because I want to make it clear that our units are going to be meters cubed or cubic meters, because we have meters squared times meters. So that's going to give us meters to the third power, or cubic meters. So now the easiest way, ladies and gentlemen, in my opinion, to do 1/3 times our 52,900 is actually to take your 52,900 and divide it by 3, because multiplying by 1/3 is the same as dividing by 3. So I think it's easiest that way. So I would take my 52,900 divided by 3, then multiply times that 146, and then I'm going to worry about my rounding. All right, now, do I want to round now? And I would say no, because my rounding, remember, is to answer the question of about how many stone blocks were used to build a pyramid. So best practice would be not to round until the very end. So here, my volume is pretty big. Let's see what I've got here. I've got a 2, 5, a 7, 4, 4, a 6, and a 6, and a 0.667. I'm going to keep it all. And if I put some commas in, so this is 2,574,466.667. This would be cubic meters for the volume of the pyramid. All right, so now I have to realize, okay, I'm not done yet. So now, remember, our question we have to answer is in green here: approximately how many stone blocks were used to build the pyramid, which means that we want to know how many stone blocks would basically fit inside this pyramid. So we now know the volume of the pyramid, how much it can hold in cubic meters. We now need to know what is the volume of a stone block. So remember, your stone block is a rectangular prism, like a box. And when we find the volume of any prism, it's the area of the base times height. Because it's a rectangular prism, that means the area of the base is a rectangle, which is length times width area. So we have length times width times height for this volume. So remember those dimensions that the problem gave us for the blocks? That would be then our length, our width, and our height. It doesn't matter which one you call which, all right? So we've got some 1.3s and a 0.7. So I've got a 1.3 meters times a 1.3 meters times a 0.7 meters. So this is going to give me meters times meters times meters, which is cubic meters. And this is actually important that both of these volumes be in the same units, cubic meters here. All right, so now let's multiply 1.3 times 1.3 times 0.7. So it looks like we get 1.183. Don't round this, not if you want to get the expected answer. All right, so this is, remember, one of our stone blocks. So now we're going to figure out, well, how many of those blocks would fit into our pyramid. Now, some of you, this math might be pretty obvious, which is a good thing. Some of you, it might not be pretty obvious what you're going to have to do. So I'm going to show you that this is really a conversion. We have two volumes, one for a pyramid and one for a stone block. And we want to end up with an answer that's in units of stone blocks. We want an answer that's units of stone blocks. So what we really want to do is realize, okay, this 1.183 cubic meters is equal to 1 stone block. That's a conversion ratio. That is a conversion ratio. So one way to look at this problem is that I'm going to take the volume of my pyramid, which is my 2,574,466.667 cubic meters, which has a denominator of 1. And I'm going to convert it into stone blocks. So I know 1 stone block is equal to a volume of 1.183 cubic meters. And I had to set it up that way so my cubic meters would cancel and I'd be left with stone blocks as my unit. So this tells me, oh, okay, then my math is to take this 2 million number and divide it by the 1.183. So that's what I'm going to do now. So if you have to type this into your calculator again, make sure you keep an eye on the screen. That's a lot of numbers to type in. Like mine, I just typed wrong. So 2, 5, 7, 4, 6, 6.667. Divide that by 1.183. All right. So now what my calculator is giving me is 217,621.8.653. And now I know this is stone blocks. Now is when I'm going to apply those rounding instructions from the original problem, which says round to the nearest 100,000, not thousands. No, if it had a THS, that would be, you know, over here after the decimal point, but it doesn't. It ends in a D. That means it's going to be before the decimal point. So now I've got to find that spot. And this is where commas can be super helpful. So I'm going to put those commas in. So my 8 is ones. This is tens, hundreds. This is thousands. This is 10,000s where the 7 is. And this is 100,000s where my 1 is here. That's my 100,000s place. So that means that I look to the next number, which is the 7, to decide, does that 1 stay a 1 or go up to a 2? So in this case, remember numbers from 5 to 9 make the previous number go up. So this is going to become 2,200,000. Everything else now becomes a 0. And that is now approximately how many stone blocks were used to the nearest 100,000. The other thing is, remember, all of these problems do require a sentence conclusion. So now we're going to have to apply this to the situation. So we're answering this question about or approximately how many stone blocks were used to build the pyramid. So it can be pretty simple. It can say, you can say about 2,200,000 stone blocks were used to build the pyramid. That is a lot. All right, so in the second problem, we have a part A and a part B. So let's take a look at the original situation. So it says an art gallery is a 6-story square pyramid with base area ½ acre. And then it tells us 1 acre is 4,840 square yards and 1 story is about 10 feet. So this is one of those situations where not all of our, the measurements that we sometimes work with are not as common as other measurements. But in some situations, when we talk about area of land, land is often described as being in acres. Like if your parents, purchase land, they'll be buying, like 3 acres or 10 acres or 100 acres or whatever it might be. So we're told that we have a base area of ½ acre. And remember, we have a square pyramid. So that is referring to the square. The square has an area of ½ acre. We also know that the height, and we can see it goes from the apex, here's our right angle, is 6 stories. That's our height. That's not a standard measurement. Stories here, we're told, are about 10 feet each. So we are supposed to figure out, notice, what is the volume of this art gallery to the nearest cubic yard? And we go, what? We want cubic yards for our volume. Yet we know a base area is in acres and a height that is in stories. So what we're going to want to do here is convert our base area that's in acres and our stories for our height into a yard measurement. Here, acres is in square yards, and we can do stories into feet here, and then we'll have to take the feet into yards. So that's what we're going to do first. So we're going to have to convert. So it doesn't really matter which one we start with. So I'm going to start with my base area. So that's my capital B, which is ½ acre. And you can write that as 0.5 if you want to. It doesn't really matter, but you might find it easier to change that. So let's do that. Let's do 0.5 for a half for our acre, which has a denominator of 1. And now we're going to multiply it times our conversion ratio. And we want to change it out of acres. So here's our conversion ratio. So we want to get rid of acres. So our 1 acre goes in our denominator, and our 4,840 square yards goes in our numerator. So our acres cancel. And now we're going to take our 1/2 times our 4,840, and that is going to give us a capital B now. That is 2,420, that is a 4, square yards. All right, there's that. Now we need to convert our height, which is in stories, into yards. So now our height, which is 6 stories, that has a denominator of 1. We are going to multiply it times our conversion ratio here. That 1 story is about 10 feet. So we want to get rid of story. And that's 10 feet, which is good because now stories are gone, but this is only going to get us to feet. So here's where we have to use the conversion ratio between feet and yards. And this is one that we are just expected to know. And we talked about this in an earlier lesson, wrote it down in case we forget, and it's not something we know really well right now. So we have to know, well, how many feet are in a yard to do this one? And so hopefully we remember that there are 3 feet in a yard. So our 3 feet is going to have to go down here so we can get rid of the feet. And our 1 yard is up here. So now our math tells us we're going to take the 6 times the 10 divided by the 3. And that looks like it's going to give us 20. So this is 20 yards for our height. Now we're going to be able to finally find our volume. So remember, you are dealing with a pyramid. So you got to remember your volume is 1/3 times your base area times the height of the pyramid. So we now have 1/3 times our 2,420 square yards times our 20 yards. It should be square yards. So now we have square yards times yards. That's our cubic yards, or yards to the 3rd power. So again, easiest way I think is to take the 2,420, divide it by the 3, and then multiply that times the 20. All right, so 2,420 divided by 3 times 20. And so here my calculator is giving me 16,133.333 and so on and so forth. So here's where we need to understand the wording of our rounding rules, nearest cubic yard. So we've talked about this wording also. Hopefully remember that if it's nearest cubic yard, cubic foot, nearest foot, anything like that, if it doesn't say any other place value, like tenths, hundredths, or 100,000s, like we were just doing, that means that we're rounding to the nearest whole number, which is the ones place. So this 3 tells us that the previous 3 in the ones place stays at 3. So this is about 16,133 cubic yards. So the conclusion for this part is the volume of the art gallery. Remember that context. Don't accidentally just say pyramid. Is about 16,133 cubic yards. Like so. All right, so for part B, there are a couple of ways we could do it. We could go back to the very beginning of the problem and like start all over from the beginning, converting everything into feet, because here we want cubic feet as our volume. But that's a lot more work than is really necessary. So what I'm going to show you here is how to take 1 cubic unit, like cubic yards from part A, and convert it to another cubic unit, here cubic feet. All right. And this is a really useful skill for mathematics, and problem solving and conversion situations. So I'm going to start with my answer from part A, which is my cubic yards. So I have this 16,133 cubic yards, which has a denominator of 1. And I'm going to convert it to cubic feet. Now, some people think, they go, okay, well, how many feet? Again, I'm doing a conversion between feet and yards. So feet and yards, well, I know that there are 3 feet in a yard. So that would this time put my 3 feet here and my 1 yard here. And they think, oh, okay, I'm done. But this is not going to work, because this yards in green is to the 1st power, and this yards in red is to the 3rd power. They don't cancel each other out. They do reduce, but they don't cancel. And so you can only get rid of one of the yards this way. So what we have to realize is that it's going to be necessary to multiply by this conversion ratio 3 times. because now we have yards times yards times yards. That's cubic yards, and they will cancel. And we also have feet times feet times feet, which will give us cubic feet. If we just done it once, not only would the yards not have canceled, but we would have been acting like feet is the same thing as cubic feet, which it's not. So now the math is telling us to take that 16,133 times 3 times 3 and times 3. Or if you want to do it fast, times 27. Oops, calculator just turned off on me. All right, let's see what we got here. So now I'm looking at 43,500, no, 400, no, okay, decimal point, 435,591. Like so. Now I put an equal sign here because, although I didn't have to round this number here, this 435,000 number, remember that I did have a rounded value for my 16,133. So that means this is still technically an approximate volume in cubic feet. So the volume of the art gallery here is about 435,591 cubic feet. Like so. So in our last lesson, yes, I think so. Yeah, that was the one where we did composite figures with pyramids, or not pyramids, with prisms and with cylinders. So now we will often see composite figures in these future lessons also, rather than doing them separately anymore. So here we actually have technically a composite figure because it is formed, so it's a crystal in context, but it's formed from two congruent pyramids. Here again is a word that we have learned before. Hopefully you remember what it means. If not, I'm going to share right now. It means that those two pyramids are exactly the same size and shape. That means they would have exactly the same volume. So we are to find the volume of the crystal in cubic feet. And so that means we have to realize that the crystal is two pyramids. So we'll find the volume of one of those pyramids, and then we'll be able to multiply it times 2, or you could add it to itself to find the volume of the crystal. But first we have to realize if we want this volume to be in cubic feet, we do have a measurement that it's in inches. 2 of them are in feet. That's good. They can stay. The inches needs to be converted. So the first thing I'm going to do is take my 15 inches and convert it to feet. So we know that there are 12 inches in 1 foot. So this is going to change to feet, and we would take the 15 divided by the 12, which is 1.25. Do not do any rounding. And again, you might want to come over here, cross that one out, and replace it with the 1.25 feet so that later on you don't accidentally use the 15 in your problem. So now I'm going to find the volume of one of those pyramids, not the crystal. So here's the volume of a pyramid. So I am looking here at, again, that 1/3 times base area times height. All right, here's where things do get a little bit more involved from the previous pyramids. The previous pyramids we had were both square pyramids, so their bases were squares. And this one is not. We have two congruent pyramids, but if you notice where they meet is not a square, it is a triangle. So these are triangular pyramids, and we have a triangular base. So going back to that information, remember at the beginning, if you need to for reference, that means your base area has to be a triangle area calculation, which means that we take the little b base edge of the triangle times the height of the triangle and divide it by 2. So remember, the base edge of the triangle would be an edge of the triangular base. That's your 3 feet. That's your little b. The height of the triangle is the measurement perpendicular to the 3 feet. Here's your right angle with the 3 feet. That makes this 6 feet the height of the triangle, the triangular base. This 1.25 feet that we converted, remember, notice it goes from the apex down to the triangular base. So this 1.25 feet, that's the height of our pyramid. That's this guy right here, height of the pyramid. So you can set this all up at once, or you can do it in pieces, I guess. It's best to just set it up all at once in most problems for accuracy. So we have 1/3 times our 3 feet times our 6 feet divided by 2 times the height of our pyramid, which is our 1.25 feet. All right, so how are we going to do, where should we start with this messy calculation? Start here. So 3 times 6 is 18. 18 divided by 2 is 9. So this is, and feet times feet gives us 9 feet squared. Then take that and divide it by 3 for the times 1/3 and multiply times the 1.25 feet. And we have feet squared times feet, which is going to give us those feet to the 3rd power, or cubic feet. So we have 3.75 cubic feet. All right, so now you got to remember that was just a volume of the one of the pyramids, maybe like the top part of the crystal. So now our crystal, its volume, remember, is the 2 pyramids together. So that means we're going to take 2 times that 3.75 feet to the 3rd power, and we get 7.5 cubic feet. So there's our crystal's volume. And that's then what we base our sentence conclusion off of. So the volume of the crystal now consider, was there any rounding anywhere in this problem? There wasn't. In the wording, it didn't say we were estimating anything. So I would say here that it is 7.5 cubic feet. I'm going to spell this one out. Like so. All right. So here we're going to see an application that makes the connection between the volume of an object and the density of that object. And you may have learned about density in one of your science classes. If not, it's not a big deal. It's all about the math here. All right. So here we're looking at a piece of pure silver. This pure silver is shaped like a rectangular pyramid with the dimensions in our diagram. And we're told in this information that this pyramid of pure silver has a mass of 19.7 grams. The question we're answering is, what is the density of silver to the nearest 10th? So not the density of the pyramid, but the density of what the pyramid is made of, which is that pure silver. And so here it's showing us the relationship between these 3 quantities. That density is equal to mass divided by volume. So here's where then we have to realize, okay, well, we're trying to find density. So that's what we want to know when we're all done. We know the mass. That's our 19.7 grams. What we need before we can figure out density then is volume. So here's where then we use what we're learning about calculating volume of pyramids to help us solve the problem. So that's the first thing we're going to do is find the volume of the pyramid. So again, remember with pyramids, we have that 1/3 times base area times the height of the pyramid. Over here, our base is rectangular, so it's a rectangle. That means base area is length times width for that rectangle. So we end up with this becoming our formula. And so looking at here, we're looking at, okay, well, the 2.5 centimeters and the 1.5 centimeters, those are the sides of the rectangle. So they'd be our length and our width. And then from our apex, our peak, perpendicular to that rectangle, that 1.5 centimeters there, that would be the height of our pyramid. So we're looking at 1/3 times our 2.5 centimeters times 1.5 centimeters times another 1.5 centimeters. So we're going to get centimeters times centimeters times centimeters. So our volume is in cubic centimeters, which is part of the standard units for density. Whether you know that or not, it's not important. We just go with it here. All right. And then we have to remember to divide that by 3 too, to get our 1/3 in there. So I get 1.875. Centimeters cubed. All right, so now that I have my volume of the pyramid, I have the last piece of my little puzzle here. So now I can find density of silver. So I am going to take my density is the mass of this piece of silver, which is 19.7 grams, and divide it by my volume from part 1 of 1.875 cubic centimeters. That's putting me there because it makes it look like another decimal point. All right, here's another thing about density if you have not yet learned about it before. Notice you have a ratio of units. You have grams over centimeters cubed. You're going to, in your calculator, divide your two numbers, but your units have to stay grams over or per centimeters cubed. So, and this is to the nearest tenth, so we'll take that 19.7 divided by 1.875. And so to the nearest tenth, we get about 10.5. And our units would be grams, and I'm going to abbreviate with my G, per centimeters cubed, like so. And then we'll write that sentence conclusion. So remember, this is the density of silver. So the density of silver is about 10.5 grams per cubic centimeter, like so. All right, this closure here says a rectangular prism and a rectangular pyramid have the same base area and they have the same height. So we have a rectangular prism, which is of course this one here. We have a rectangular pyramid, which is this one here. We're told that they have the same base area. So that means we can kind of see here, it looks like they're rectangles, maybe squares. So these areas are the same. We're also told that they have the same height as one another. So the heights here and here are both the same measurement. So this wants to know, well, how much larger would be the volume of the prism than the pyramid? And explain our reasoning. So sometimes math can help you with your reasoning here. So if you're trying to figure out how much larger one quantity is of another, then the easiest way to figure that out is to do the inverse of multiplication, which is division. So when you're figuring out how much larger one volume is than another, it's like if I take the smaller volume times this number, I would get the bigger volume. If I take the smaller volume times a certain number, I would get the bigger volume. That's what it means by how much larger is one volume over the other. So if I take the volume of my prism, which is base area times height, and I divide that by the volume of my pyramid, and notice I am just doing the general. This is 1/3 times base times height. Here, the capital B's are factors that would reduce to 1. The H's are factors that would reduce to 1s. So now what I have is 1 divided by 1/3. Here's a little bit of basic math review. Remember that this would mean 1 divided by 1/3. So what was that procedure again for how we divide by fractions? If you recall, you change division to multiplication and you do the reciprocal of what you're dividing by. So this becomes 1 times 3, which is 3. And so what this tells us is that the volume of this prism is 3 times larger than the volume of the pyramid. So the volume of the prism is 3 times larger than the volume of the pyramid. Understanding and practicing with problems like this helps us develop our reasoning, our mathematical reasoning skills, and just reasoning skills in general. All right, so that does finish up this lesson for us today.